Thanks for watching our presentation. I'll talk about SCA, a secure CNN accelerator for both training and inference. My name is Lei Zhao. I'm a PhD candidate in the University of Pittsburgh. I work in the areas of computer architecture, domain-specific accelerator design, and secure and privacy-preserving machine learning. Neural networks are already widely deployed in our mobile devices. For example, neural networks are used in facial recognition to unlock our screen. Neural networks are used in speech recognition when we ask for voice assistance, like Hi Google or Hey Siri. There are countless other use cases in our mobile devices. However, its security issue has not been fully resolved. Take the example of selling a cell phone to a consumer, who may be an adversary and hacking to the phone to steal the model. Encryption may help protecting the weights in the storage, but for the case of in-device training, updated weights need to be written into storage in each iteration. Frequent encryption and decryption on this large amount of data can cause big computation overhead and long latency. Our work uses stochastic computing to achieve cheaper computation in mobile devices. We also utilize the precision loss during the format conversion process as a hardware fingerprint to protect the weights. For example, device A and device B have different precision when converting the same value. In this example, 0.6 is converted into 0.65 and 0.58 on device A and device B respectively. Weights are stored in different formats in on-chip and off-chip memories. The binary format weights in off-chip memory can only produce inaccurate results if used directly in neural network computing. Weights need to be converted into SC formats to achieve accurate results. However, it requires the format conversion to take place in a specific device. Now let's take a look at some background of stochastic computing. SC numbers are represented by the probability of ones in the bit stream. For example, 0.75 binary representation is 0110. When converted into SC formats, it is represented in the bit stream with 75% of the bits being 1. The addition and the multiplication can be implemented by using simple mux gates and XNOR gates. We use EDRAM as our on-chip buffer. A EDRAM cell is consisted of a transistor and a capacitor. We can abstract the capacitor as a leaky container that stores electric charges. The bit stored in the cell is determined by the amount of charges in the capacitor. Because the capacitor leaks charge over time, it requires periodic refresh operations to retain its data. Otherwise, the bit may be flipped. To generate device-dependent SC bit streams, we select some rows in the EDRAM buffer as victim rows. When the system starts up, all the cells in the victim row are pre-charged to store 1. Then we reduce the refresh frequency to a predefined value, so that approximately half of the cells flip to 0 because of the charge leakage of capacitors. Then we read out the whole row, which is a bit stream encoding a binary value of 0.5. The final step inserts zeros or ones into the row to reach the target value. If the target value is smaller than 0.5, we insert zeros, otherwise we insert ones. Because the position of the ones in victim row are determined by the distribution of the weak cells, which is a device-dependent information, the generated bit stream can be used as a hardware fingerprint, which is unique for each device. In order to embed this hardware-specific information into neural network model, we use the SC format weights in forward propagation and calculate the loss, while we still use the binary format weights in back propagation and the weight updates. In the next iteration, we start over again from the format conversion. To test the security of this protection scheme, we first train the model on device A, which is also our target device. From the second column in the table, we can see negligible accuracy loss if the model runs on the target device. But if we use a model in another device B, as shown in the third column, a significant accuracy loss can be observed, because device B has a different precision when converting the same set of weights. The last column shows that if the binary weights are used directly in computing, the model still only generates inaccurate results. The protect capability comes from the difference of the two formats to represent the same set of weights. However, since the neural network are typically over-parameterized, they are also capable to learn this difference if they are overfitted. As shown in this figure, accuracy stops increasing, but the distance keeps dropping. To make the model only learn the intended task instead of the difference between the two formats, we change the offsets where ones and zeros are inserted. To avoid the sudden change of the entire model's precision, in each epoch, we only change a single layer's insertion offsets. On our 6 tested benchmarks, when the model converges, the distance also stops decreasing thanks to the dynamic changing insertion offsets. In stochastic computing, there are 2 ways to implement addition. The max-based adder has a smaller area footprint, but can only output 1 bit each cycle. Its precision is also significantly lower than its counterpart, the approximate parallel counter-based adder. An APC counts the number of ones in the bit stream with some approximation in the first few stages, so its output is in binary formats. Although it has a higher precision, its logic is more complex. We use a mixed adder design. After the XNOR-based multiplication, we first use mux-based adders to reduce the number of bit streams. Then we use APCs and an adder tree for following additions. Our experiments found a 4-input mux-based adder can meet the balance of area, footprint, and accuracy. Mux-based adders have low precision because most of the bits are discarded. So we can use a concatenation to substitute the muxes if we use a shorter bit stream at the beginning. This not only decreases area, but also reduces computation because of shorter bit streams. The SCA accelerator contains both an EDRAM buffer and the SRAM buffer. All data stored in off-chip memory and the on-chip EDRAM buffer are in binary formats. The SC conversion unit uses the victim rows from the EDRAM buffer to convert the data into SC formats and store them in the SRAM buffer. Because of the APC in the MAC unit, the output is in the binary formats and stored back to off-chip memory. Whenever data are stored off-chip, they are in binary formats, so they are being protected from being stolen. We developed a CNN framework to support stochastic computing. We changed all computation in the CUDA kernels to bitwise operations. We tested 3 datasets with both multi-layer perceptron and CNNs. AEP is a baseline that uses hardware error as a fingerprint to protect models, but not using stochastic computing. SCCNN is another baseline that uses stochastic computing, but no protection. SCAR1 is our scheme with only protection support. SCAR2 is our scheme that also uses optimized MAC operations. The performance is normalized to that of AEP. SCAR1 achieves 11.7 times speedup by using our victim row-based SC conversion. Thanks to the optimized MAC operation and shorter bit streams, SCAR2 achieves 34.2 times speedup. The energy consumption is also normalized to that of AEP. SCAR1 and SCAR2 achieves 94% and 98% energy saving respectively. At the conclusion, mobile devices have a requirement for protection and fast computation. We use SC simple logic to achieve faster computation. We also use the precision loss during SC conversion as hardware fingerprints to protect weights from stolen. Our scheme also supports in-device training. The experiment results show the effectiveness of our protection scheme with significant speedup and energy saving. Thanks for watching, and I'm glad to answer your questions.